Our lesson for today is 8.4a, Stretching and Shrinking. Essential question: how do you write an equation when the graph is stretched or shrunk? So the transformation we are talking about today is dilation. A stretch will cause our graph to get tall and skinny, and a shrink will cause our graph to get short and wide. So now if we look at the butterfly pictures below, this first one here is the original. And we need to decide what happened vertically to the next. Looking at the butterfly in the middle, it looks as though it has been pulled up and down or made taller, which would be a stretch. The butterfly on the end, on the far right side, looks like it's kind of been squished from the top and the bottom, which makes it a shrink. In this first example, we are asked to make a table of the function given just the graph. When x is -2, it looks like y is up at +2. So we can fill in the table as we go. -2, +2. When x is -1, so left 1, so like here, it looks like y would be here at 1. -1, +1. And then x is 0, it looks like y is also 0, 0, 0. X is over at 1, which looks like hits right here nicely at +1 for y, so 1, 1. X is over at 2, y is up at 2, so the point 2, 2. The V shape of this graph should tell you that it is absolute value. And it looks like the parent function, it doesn't have any transformations that look like has taken place. So our equation would be y equals the absolute value of x. This next example also looks like its absolute value. We'll worry about the equation part after we fill in the table. So let's start by finding nice points of intersection. So when x is -2, it looks like y is up at 4, so that would give us the point -2, 4. Remember, the x-axis is the one going left and right, and the y-axis is the one going up and down. And then we always write our ordered pair, x, then y. Alright, so next one looks like if I go to where -1 would be, and then go up, it hits nicely at 2. So that would be the point -1, 2. And then 0, 0. So 0, 0. And then if I go over 1, looks like it's hitting nicely at 2. 1, 2. And then if I go over 2 and up 4, that's nice. So 2 and then 4. To figure out the equation for our absolute value function, we need to figure out if there was a stretch or a shrink. So if we look back at this first one that was the parent function, it looks like from 0 we go up 1 and then over 1 to this point here. This tells us that there would be a stretch or a shrink of 1, which in our equation would be represented right here. That doesn't actually change it at all, it's just 1 times it, so this one has no stretch or no shrink. In this next one, from 0, 0 up to this first point here, it looks like it goes up 2 over 1. So this will give us a stretch of 2. In our equation, we would write that in the same spot we did up here. We still have y equals and the absolute value of x, only now we need to incorporate this 2 to show our stretch of 2. So y equals 2 times the absolute value of x is our equation. There's another way to find this missing value, this stretch or shrink, which we call an a value. It'd be, you take your equation, y equals a times the absolute value of x, and we plug in a number for x and for y. So in this case, I could choose to use 2 and 4. 2 would be my x. I'm going to put a 2 here. And then 4 will go where the y is. and then we solve for a. So 4 equals a times the absolute value of 2. We know to find the absolute value first. So 4 equals a. The absolute value of 2 is 2 absolute values. A distance, so it's positive. And then a times 2 is just 2a. So 4 equals 2a. Balance, solve, divide by 2 on both sides. A equals 2, which is what we got here. For this next one, we're going to go ahead and start by making our table first. So it looks like if x is -4, y is up here at 2, so that'd be -4, 2 for our ordered pair. -4, 2. And then looks like it hits nicely if I go -2 up 1. So -2, 1. And then 0, 0. Again, we're just looking for nice points of intersection. Over 2 up 1. Over 4 up 2. So now from 0, 0, it looks like it goes up 1, over 2, where it hits nice again. So this should tell us that our a value should be 1/2. Let's go ahead and plug it into our equation like we just did for the last one. Remember, this is an absolute value function. So y equals a times the absolute value of x. And let's plug in a point. I'm going to just go ahead and use this point right here for 2. So that means 2 goes in for y. And we don't know what a is, so we're solving for absolute value of x, which is 4. I take the absolute value of 4, which is 4, so 2 equals a times 4. A times 4 is just 4a. So 2 equals 4a. Now I need to get rid of that multiplying by 4 to get a by itself. To do that, I will divide by 4 on both sides. 2 over 4 is the same thing as 1/2 equals a, which is what we got over here. So our equation is y equals our a value, which is 1/2, times the absolute value of x. How do we write an equation that shows dilation? Dilation is the stretch or the shrink that's happening to our graph. We can write that as a times whatever our function is. So the a value is whatever is out front of our equation. And if a is bigger than 1, it is a stretch. But if a is less than 1, it is a shrink. Now this is not including negatives. Remember, if there's a negative out front, that actually causes a reflection and our graph flips over the x-axis. So when determining the stretch or the shrink, just look at the a value as a digit, like just the absolute value. So if it were negative, that's telling you it's a flip. If it were, for example, 1/2 or 0.5, like in our example before, it's a shrink. Determine what happened to the following functions. So in this first one, we look at it, y equals 3x squared plus 5. That little 2 tells you that this one is a quadratic. Which, if you remember, on a graph, it looks like a U shape, which is also called a parabola. Now we can look at the equation and see each thing is causing a different transformation to what would be the original parent function. This 3 out front right here is in the same spot where the A is, which tells us it's a stretch or a shrink. 3 is bigger than 1, so it is a stretch. Stretch of 3. Next we see the plus 5 on the outside, which tells us it goes up 5. And those are all of the transformations that is happening in example A. In example B, we see the bars, which tells us this is absolute value. The shape of absolute value is a V shape. And now we list the transformations. See this negative out front right here? That tells us that there is a flip or a reflection over the x-axis. And then we see this 1/2 out front. That's our A value. And 1/2 is less than 1, so we have a shrink of 1/2. Lastly, we see we have x minus 2 inside the bars, which tells us our graph moved right 2. Right 2. Let's take a look at example D. This type, it says y equals 4x minus 2. That is linear. And the shape is a line. We can still look at this as transformations even though we know it's a straight line. 4 is our slope, but if we're looking at this as transformations, it's where the A value is in the equation, which is a stretch or a shrink. 4 is bigger than 1, so that tells us that we have a stretch of 4. Stretch of 4. And then the only other thing we have is the -2 or -2, which is actually our y-intercept, which tells us that it went down 2. And this concludes our lesson 8.4a.